Thank you. As Itai said, I'm Nate Sweet, and I'm a software engineer on the managed Kubernetes product for DigitalOcean. And I am also the creator and co-contributor, along with Lorenz Bauer at Cloudflare, of the new tools eBPF library, which is now in the process of being slowly ported over to the Cilium organization under the same moniker. It's a Go-only library with no C bindings, and it comes with an assembler and debugger. Cloudflare has been using it in production for the past year and a half or so. And if you are embarking on an eBPF journey yourself, Lorenz and I, and Joe Stringer, who is also here at the conference for Cilium, would be gratified for any pull requests you might want to give us. He and Lorenz actually deserve most of the credit for that library being great. So I wanted to plug that just because, we're trying to get some hits on that. So, all right. So, understanding and troubleshooting the eBPF Datapath with Cilium. Why should we care? The network is the bottleneck. And I'm assuming most people in here know that the network is the most time IO-bound thing you can do. But I think something that's new that people haven't talked about so much is that with the advent of the public clouds, writing distributed systems has become incredibly mainstream. And we are largely running those distributed systems on software that was designed in the 1970s. And so getting insights, determinism into your network, it's really hard. The tools that we have now are kind of unwieldy. So I think that eBPF is an interesting step forward. I don't think it's necessarily the final solution, but I think it's a powerful tool, and I think as we'll see, it offers quite a bit in terms of flexibility. The other reason this is worth learning about is eBPF is kind of spreading everywhere. The Linux net devs seem to enjoy putting it everywhere they can. So whether or not we want to learn eBPF, I think we're going to see Linux kernels that get built in the coming years that don't even have NetFilter in it anymore and solely rely on eBPF. I know that that's something Cilium wants to do, is offer zero IP tables CNI, which is an interesting proposition. And the third reason is that metrics are money. There was a great talk at the Paris Kernel Recipes Summit this year by a guy named Aurélien Rougemont from Synesthesio. And he had some great debugging war stories. I linked to the talk in the slides if you want to look at it. But he makes this really good point that people don't really want to worry about this stuff, right? Even if you are interested in systems programming, you want to solve interesting problems. You don't want to understand why the UDP socket buffer maximum got hit in your kernel distribution. I mean, maybe you do, but if you do, you're kind of weird. And so getting this stuff done quickly and efficiently means more money for you, means more money for your organizations, makes your products better, allows you to focus on problems that actually matter rather than tuning the Linux kernel. So, okay, what is eBPF? I'm hoping that there's some familiarity with it, but I'll do just kind of a quick primer in case you're not. eBPF stands for Extended Berkeley Packet Filter, and this is an example program of such here. This is an XDP program, which stands for Express Datapath. And Express Datapath programs can be attached directly to network devices. And specifically, XDP programs can do things like drop, pass, and redirect packets. And it can do these things very efficiently because it's run almost immediately inside the kernel data path. So in this example, this program example is taking any packet that's an ARP packet and dropping it if the source IP of the ARP packet is contained inside this blacklist. So we get this data structure, we cast the void pointer to an Ethernet packet, we check the Ethernet protocol. If it's ARP, or if it's not ARP, we pass it, so that means continue along the data path. Otherwise, let's cast the offset of the Ethernet packet into an ARP packet. We look at the source IP of the ARP packet. If it's in our blacklist, we drop it. If it's not, we continue on down the data path. So I hope this is kind of a helpful illustration of what eBPF is. It's programs and maps. And this visualization hopefully helps a little bit as well. We have a program running inside the kernel. It's doing something, and it shares a map structure with user space. That map structure contains the maps that eBPF offer are quite extensive. You can have CPU-bound maps, so it's a data structure per CPU. So if you're doing receive channels on multiple CPUs, the CPU data structure the data structure lives on each CPU, which obviously translates into quite a bit of performance. And then it can also just have configuration data, right? Like, I don't know what a good example would be, but these protocols get dropped or something like that. So why eBPF? eBPF is fast. It's a very compact amount of logic in a tight space, and that lends itself to being quite fast. It's also just-in-time compiled, so I don't know how many people know this, but there is a compiler in your Linux kernel that compiles bytecode into raw ARM. There's actually a RISC-V compiler now for eBPF. Whoever wrote that is a brave person. And eBPF is flexible. And what do I mean by this? eBPF is just generalized code, right? It can be C code. There's a Rust compiler, so you can write in Rust if you want. It wouldn't surprise me if someone writes a WebAssembly version of it, because WebAssembly is everywhere now. So yeah, the flexibility that it allows is quite enormous. And for example, the XDP program, the Linux kernel only cares about the return of pass, drop, and redirect. But within your code, you can kind of do whatever you want. It's basically a microservice within the kernel. And finally, the eBPF separates data from functionality. I think that's a really big argument in its favor. I hope everyone here appreciates why separating functionality and data is a very powerful construct. Certainly, we can achieve some of the things that eBPF can achieve with things like netfilter and IP tables, and you can even track some amount of state with those things. But I think that it's a lot easier to create data-driven stateful applications with eBPF rather than a ginormous IP tables chain. And I'm just going to touch a brief history of eBPF, because I said I would do that in the abstract. So the paper that kind of kicked this off was by Stephen McCain in 1993. He wrote this paper called the BSD Packet Filter. It's actually a really good read. It's very, I don't know what's the word I'm looking for. It's an accessible read, so you don't have to be a Linux kernel dev to understand what he's trying to drive at it in that paper. And he based this idea on the idea of packet filtration, which had been around since the 70s. But he was like, well, what if we put compilers and networks together? And that ended up being a pretty bright idea. Previously, packet filtration was more of an abstract concept. You operated on known packet types and their fields rather than having access to the raw bytes. Just as an aside, I was kind of curious. People talk a lot about the history of this idea. Where did packet filtration come from? And it seems like everyone was citing this paper that I just threw up by Jeffrey Mogul in 1987, wherein the Xerox Alto is labeled as being the first packet filtration computer. And I was really curious, is that true? And indeed, he does cite that the Xerox Alto in '76 was the first computer to have this. And I was curious, since everyone's citing him, what's his source? And, you know, that's kind of an academic faux pas. So I dug a little further, and this turns out to be right, because David Boggs invented Ethernet. So Indeed, the Xerox Alto was the first computer to have packet filtration. Okay, so what is Cilium and why should we care? eBPF is easy to look at and understand because it's flow control in C or Rust or whatever you're writing, but it can be very difficult to configure, maintain, operate with. And so having a hardened wrapper that has all of this stuff built into it is, I think, quite useful. And Cilium is a good general purpose wrapper that gets you 99% of what you need when you're dealing with distributed systems. And if you're familiar with Kubernetes at all, the object names are very familiar, and in fact, they're pretty much identical. And then as of 1.6, Cilium is both a CNI and a drop-in replacement for kubeproxy. So you can kick kubeproxy to the side if you're running Cilium 1.6 or greater, which is nice because kubeproxy can ping the API server quite heavily. IP tables rules, even if they're not running, actually can slow down your data path, and so it can be very nice to get rid of all that stuff. All right, so the next 6 slides, I'm going to walk through the kernel data path, and we're going to start at the hardware, and I'll try to highlight where Cilium enters the fray. Hopefully it kind of makes sense as we go along. I'm not going to focus too much on the hardware because we don't really need to know too much about it. Obviously, it isn't useless to know this stuff either. So I'm going to skip some of the steps here and just kind of focus on what happens when the driver is initialized and packets are flowing. So the network card gets assigned a direct memory access region in RAM. The Linux kernel gives it that address space, and then when the network card receives the packet, it sends it up to the memory through the PCI bridge into something that effectively is like a ring buffer. And then this generalized pull mechanism in the Linux kernel called the NAPI pull mechanism, which is used by ePull and the drivers and lots of, basically anything that's doing asynchronous work can use this generalized pull mechanism in the Linux kernel. It's listening for these packets and then it's processing them as they come in. And so then we hit the CPU. All right, so then we hit layer 2. Most drivers, or all network card drivers, implement a pull this interface into this pull mechanism, and they do lots of different things. But sort of the biggest thing they do for our purposes is they can call into our first BPF program, which is XDP. This is where Cilium's network policies lived, so this is where we can drop packets, and this is where we can cut off a lot of work at the pass. If the XDP program passes and says this packet is good to go, we move on to the next function that the driver pull function will call, and that is cleanRx. And this is where the Linux kernel allocates a socket buffer for the packet. Socket buffer isn't maybe the best name for what it is. That makes you think oh, there's a socket and it has a buffer. It's just the generalized data structure that wraps packets. And then finally, we go into the general receipt offload queue. This is a software implementation of a hardware specification called large receive offload. And what this does is if you have it enabled, you can trade a little bit of latency for a lot of throughput. And the packets will aggregate and grow and go into a generalized queue that then will get processed. So if you ever run TCP dump and you've seen undescribably large packets coming in, it's probably because you have GRO turned on and the kernel is giving you fake huge packets. I'm not going to focus on that too much because the more important part is getting into receiving the socket buffer and kind of going up the layers. So we call into receive socket buffer, and this is where we can finally start to differentiate between layer 2 and layer 3. So when we call receive socket buffer, if the network card driver hasn't implemented XDP, which a lot of them haven't, although the list is growing quite extensively, then XDP will get called here. Again, Cilium's network policies tend to live here. among other things. The next thing that we do is if there are some kind of tap interfaces, receive socket buffer function will send the packets into some of the tap interfaces. We don't need to worry about taps for Cilium because there are none, so we move on to the traffic classifier. The traffic classifier, if anyone's worked with Q disciplines in the Linux kernel before, the traffic classifier can kind of deal with these. It can do some routing, it can mangle packets, it can drop them, and it can drop them in a way in which it may or may not influence the overall statistics of a classifier or a queuing discipline, which is really useful when you're trying to do generalized traffic shaping. One second. Finally, we hit the layer 2 net filter. Again, I don't even think that kubeproxy deals with the layer 2 net filter. Cilium doesn't. And so the next thing that we do is we move on to whatever the network device's default protocol is. 99% of the time, that's IP or IPv6. I don't know, maybe some of you are running AppleTalk, but I doubt it. So we have IP receive, and the IP receive is, I hope that you can see that what we're doing is we're decapsulating, right? We're truncating the layers and we're kind of trying to move up the stack. So IP receive gets called, and the first thing that happens is we call net filter pre-routing. So if you've ever written IP tables pre-routing filters before, this is where they exist, and they can drop a redirect here. We call IP receive finish. We go into the routing package. Cilium will use the routing package if you're not tunneling. So what that helps to do is that helps to short circuit the data path and move packets down into the VETH pairs a lot more quickly. And then we call net filter post routing. These two net filters, I think, are the things that could potentially go away in the future. So if you can imagine this flow diagram that I've created without any of the net filter squares, that could be a possibility in the future. And finally, we get IP local deliver. This is actually the protocol aware function. So is this TCP or UDP? Or maybe it's some other defined protocol that we don't know about. There are other protocols that the kernel can call into. They're usually kernel modules though, so we don't need to really worry about them. And then we hit the transform policy, and this is where things like IPsec-live, UDP, decapsulate, things of that nature. And then finally, we reach a layer 4 protocol, and I'm gonna focus on UDP because I don't want to chase the TCP state machine around the Linux kernel because it's quite unwieldy. So imagine that it is TCP, and it's a useful lie, I guess. So we receive our UDP packet, and now we have a port number. We finally have something that can map us into user space. And so we're nearing the end of the bottom half of our work here. UDP receive finds the socket. It goes through one more transform policy. The layer 4 protocols can go through transform policies. For the Cilium CNI, they do not. And then the sockets have two data structures. They have a receive queue, which is just a list of the socket buffers that are waiting to be processed in user space. And then it has a wait queue. And if you remember that NAPI pull mechanism, that is the data structure that the different pull mechanisms inside the Linux kernel can use in order to route the packet up into user space. So we push our socket buffer onto the receive queue, and we flip this special bit in the wait queue. And now we're nearing the end of our packets journey. So this is a socket listening program. It doesn't have any error checking or whatever, and the ePoll part of it isn't really, strictly speaking, necessary because receive can do polls for UDP. But again, pretending that this is like kind of what we need to do, we allocate a socket, we create an ePoll instance, we add the socket to ePoll for listening for receive events, and then we ePoll wait. We ePoll wait, and then when that wait Q bit gets flipped that we talked about, the NAPI mechanism wakes ePoll up, and then it comes back out of user space. Well, first it populates the events you're listening for, or errors out, because sometimes ePoll is wrong. And then you come out of user space and you can start processing your packet. In this case, we're doing UDP receive message. And so UDP pops the packet off. So we're calling a syscall now. And UDP receive message pops the packets that we want to process off of the socket's receive queue. And then it runs them through 2 more BPF programs. The first one we are concerning ourselves with is the C group eBPF program. This is pretty cool for Cilium. This allows for transparent client-side load balancing. So if you've ever done client-side load balancing, you know that your application needs to be aware of it, and you're just kind of doing it yourself in the application space. Cilium has a configuration thing that you can turn on that allows you to do client-side load balancing that's completely transparent. So you're hitting some load balance service in Kubernetes, and Cilium can load balance via policy for you. Yeah?
This is where the kubeproxy replacement kicks in?
kubeproxy replacement, there's a lot of things that finally had to happen for kubeproxy to get replaced, but I think node ports was the biggest one, which I think would be a little bit higher up the stack. But there's a lot of stuff that it's doing. If you were following along with that saga, you would look at your IP tables rules that kubeproxy had generated, and you would notice that none of them were being used, except for a handful. And then as Cilium got matured and matured and matured, fewer and fewer of them were being used. But yeah, trying to think, what made you say that? Why?
The reason I was asking is you were representing this as an internal load balancer sort of mechanism, and so I was thinking that that's probably how implementation actually ends up landing.
Oh yeah, no, that makes sense. Sorry, the reason he said that is because he said kubeproxy does do, with IP tables, it does some of this internal load balancing on the node. My impression is that kubeproxy does a lot of that when it's receiving, though, correct? Oh, so this is more when you're egressing, right? You can do transparent client-side egressing load balancing, which is, I think this is how, I think Cilium and Envoy work really well together in this instance. I should say the Cilium guys told me to say that. I don't actually know why they told me to say that. I don't know anything about Envoy, so. Okay, so our final BPF program is socket operations, and this is really useful for traffic shaping. So if we were dealing with TCP, although there is some stuff it can do with UDP, we can do really fine-grained traffic shaping at the socket level. So this client over here for this server gets less bandwidth than this one over here, is the kind of thing you can do with sock ops. And then finally, we reach the end of our journey, and we have a buffer in user space. All right, so this is kind of an interesting map of Kubernetes networking objects to Cilium networking objects to then kernel primitives. So there are more networking objects, I realize, in Kubernetes than what I've listed here. But these are the primitive objects. So for example, load balancers are node ports and cluster IPs, which in turn are just service objects. And so those map pretty cleanly onto Cilium service objects. Cilium is, I mean, you see what I was saying about the names being quite similar. So this chart looks good, but unfortunately the whole story with this chart is more complicated because Cilium is actually pretty complicated in its implementation, and there are 2 really big reasons for this that are worth dwelling upon momentarily. And the first one is that the data path is complicated, and the data path can change based on the version of the Linux kernel that you're running. So the BPF programs weren't all there in the beginning. So for example, the C group BPF program is quite new. And so there are lots of different ways of doing traffic shaping. Maybe in this version of the Linux kernel, there are drops happening in the traffic classifier rather than XDP. I actually don't know if, I don't actually think that's a great example because I don't think that happens, but that's a kind of example of what might be happening, is that the data path chart can kind of shift. And then the other reason this is complicated is that, well, what I was kind of talking about is just the shape of the data path changes based on your application logic as well. So depending on the policies that you implement, they may or may not be implemented in these various programs. So, all right. So, I'm going to pull a little bit of a bait and switch. I hope the title slide kind of indicated this. I titled this talk Understanding and Troubleshooting, and my goal is to kind of, my goal and like the slides are available to download and you can use them, and I think we're going to try to release them under a Creative Commons license if people want to play with them or add to them or change them, although they'll be out of date in like 6 months probably. Yeah, the goal was more understanding, and the troubleshooting part is more just understanding what's available. So I think the most useful resource really is the Cilium Docker image itself. So if you're running Cilium as a CNI in the Kubernetes cluster, execing into the Cilium, one of the Cilium daemon sets, gives you a lot of power. And the two most useful tools in that Docker image, I think, are the Cilium CLI itself, which has a lot of functionality in it for debugging. And then the second one is BPF tool, which is the tool that the Linux kernel devs wrote to deal with BPF. And one reason it's so cool that the Cilium Docker image has it is that it's not mainline packaged with any of the normal distributions right now. So if you're running Ubuntu, if you're running whatever, you can't apt-get BPF tool right now. There is a PR to get it into Ubuntu soon, but it's there in Cilium, which is a good thing. So I have a little kind of video to show. Maybe what I can do is mirror. So what we have is we have this service in Kubernetes, and it's throwing lots of 400s. It's a load balancer with a deployment. And, oh shoot, sorry that it got truncated there. Let's see if it, so we have this service, and I'll just tell you what's happening since it's getting truncated. I'm about to exec into the Cilium pod to see what's going wrong with it because the service is just throwing 400s. So we're going to exec into it. This is really unfortunate. The person next to, oh yeah, that's a good point. Good call. Really? Okay, where am I in this thing? Okay, so basically what happened is I exec'd into the Cilium pod, and I ran a command called Cilium endpoint list. And what that did is that listed all the endpoints on that node. It showed if they had ingress or egress policies attached to them, and then it gave me an endpoint ID. And now what I'm about to do is I'm about to run a program called Cilium monitor. And Cilium monitor is basically like TCP dump. It allows you to monitor specific sockets even within one endpoint, or just specific endpoints themselves. So now I'm getting a hex dump of what's going on in this application. And there's lots of great stuff that you can look at. Like it's protocol aware, so it knows that the connection has been acknowledged and connected. And looking at the hex dump, I see that proxy protocol is enabled on the client side, which that was our issue, yeah. We're using no proxy, and we should be using proxy. So let's fix that and get rid of, make the server proxy protocol aware. We redeploy it, and I bet this is gonna work now. Hey, it's a pre-recorded demo. So yeah, and then the other tool I want to really highlight is BPF tool. So it ran a little bit fast, but basically I ran the command BPF tool net, and it dumped all the BPF network device programs that are attached. So if you look at that list output, you'll see that there are network device names, and then there are other things which are really useful. Specifically, there is the name of the program that's actually attached to the network device. So we can go into Cilium's repository, go into BPF, look for the name of the program. The section name of the program is in there. We can look for the section name, and that's actually the actual BPF code that's running on that device. I think that's really useful because first of all, I think that's easier than looking at a giant IP tables chain. But if you're ever dealing with something with Cilium, you can easily take a look at the logic just by running that command. So that was a couple of steps. Okay. And I think that's all I have. Oh, no, I have one more thing that the Cilium guys wanted me to say. So they just dropped a new open source tool. Maybe a lot of you saw that this week, called Hubble. And it actually is a web UI that does a lot of this stuff. So you can get really fine-grained insights into your network down to a very, very granular level. And see why and where drops are happening. You can look at where the policies are taking effect and kind of get better insight into the full data path of your network. And that's it. Thank you very much.
Thank you, Nathan.
Yeah.
We do have a couple of minutes for questions.
Yeah, if anybody wants to ask questions, I'm fine to stick around. Otherwise not.
Yeah.
Hi, I have a question that's kind of more general to BPF. So we're running a lot of logic inside of the kernel or resident to the kernel. And I'm curious on, if there were a bug and a compromise of that bug, you'd effectively be running in ring 0, getting full control of the system. So I'm just wondering, what does the kernel provide that's doing, some protection against, say, a rogue code that's running in BPF?
That's a really great question. So I think everyone probably heard that. So there is a verifier in the compiler, but I think that's a really good point. I mean, that's why I said eBPF is a good step forward. I don't think it's the end goal because, yeah, making your interface raw bytecode isn't really secure, right? So I am really interested to see if we can come up with better solutions. The network is really hard to get right, and it's very understandable why people want this mechanism because it just provides a level of flexibility like an order of magnitude greater than what we have. But in some ways it is a step back because, yeah, some of the worst security headaches of the last 2 years have come from BPF. So it's a trade-off, but the NetDev mailing list won't have it any other way, so.
Yeah. Just a second.
So you showed a code segment where the actual code was put into the kernel, right? Say if it had a problem in the code what was written, would it crash the kernel?
So The verifier will probably, I mean, I'm not going to say you couldn't crash the kernel. I think it'd be really hard to do because, for example, it doesn't allow you to execute more, like this is configurable at compile time of the kernel, but I believe it won't allow you to execute more than 40,096 instructions per program. And then the maps are also severely constrained, right? You have to tell, before you run the program at compile time, you have to say how big this map can get. So the programs are quite deterministic. I'm sure that there's a way to mess it up if you really wanted to, but I would venture to say that that's a pretty, I would say it's pretty safe. And it's also why I think, it's also why it's good to use something like Cilium and good to use open source code, right? Because it's being used in production by a lot of people, so.
If we already have a net filter hook module out there, would it be better to use eBPF?
If you already have a what module?
A net filter hook kernel module.
If you already have a net filter kernel module, would it be better to use that or eBPF? Is that the question? I mean, I guess it just depends on your use case. Yeah, I would need to know more about what the exact use case is in order to weigh in on that. I don't know. It's a good question. Yeah, to be clear, I don't want to like stand up here and say that eBPF is a panacea, right? The right tool for the right job. Definitely don't just throw don't throw everything out the window. IP tables is still good, and it's been around for a while.
Yeah. One more, and then we can approach the stage.
Do you think if I'm nowhere near needing the performance, I'm nowhere near running up into IP tables performance issues. So is the tooling, and I couldn't see it too well, I'll go check it out later,
Yeah.
but is like the tooling, are you saying even independent of performance, is the tooling there that it would be compelling for me to do it this way, independent of performance?
I actually do think that is one of the unsung benefits of Cilium, is that it is quite easy to use. I personally think it's easier to grok sometimes than looking at a giant IP tables list. It's easier to find problems sometimes. It is kind of a one-stop shop, whereas sometimes you're messing around with lots of different net tools in traditional Linux. Yeah, I will defer to my earlier statement of networking is hard, though.
All right, I want to thank again Eitan, and
right.
don't forget to,
you.
yes, we can clap.